Welcome to Fact Flow today, a journey into one of the most mysterious and unreachable places on our planet, the Challenger Deep. In this video, we will explore the history, science, myths, and modern discoveries surrounding the deepest known point in Earth's oceans. From ancient misconceptions to cutting-edge technology and record-breaking dives, the Challenger Deep challenges everything we thought we knew about life, pressure, and the hidden world below. Get ready for a gripping descent into darkness where science meets wonder. The story of the Challenger Deep begins long before humans understood what truly lay beneath the surface of the world's oceans. For centuries, sailors, natural philosophers, and early scientists believed the deep ocean floor was mostly flat, lifeless, and featureless. People imagined it as a silent, dark desert stretching endlessly beneath the waves, a place where pressure and cold would make the existence of any life impossible. These ideas shaped the world's understanding of the seas for generations, until a single expedition shattered everything. In the late 19th century, the British embarked on what would become one of the most influential scientific missions in human history, the voyage of HMS Challenger. This was not a warship or a vessel designed for conquest. It was a floating laboratory carrying naturalists, chemists, physicists, and oceanographers. Their mission was simple, yet revolutionary: to study the world's oceans in a systematic, scientific way. Before this, there had never been a global survey of the seas. The team wanted to understand temperature, currents, biodiversity, and, most importantly, depth. As the crew traveled across the globe, dropping weighted ropes into the ocean to measure how deep the seafloor lay, they discovered an underwater world far more complex than anyone had imagined. The ocean was not flat. It was carved with underwater mountains, plateaus, and chasms deeper than anything that existed on land. And then, in the western Pacific Ocean, they encountered something extraordinary. While taking measurements near the Mariana Islands, the HMS Challenger crew recorded a depth unlike anything ever seen before. The rope kept sinking, falling deeper and deeper into the darkness until it reached a point more than 6 miles below the surface. The reading stunned the scientific world. No one had believed such depths were possible. People debated whether the measurement had been mistaken, whether the rope had snagged on something, or whether the ocean truly hid such an abyss. But the data held strong, and soon the world learned the name of this place, the Challenger Deep, honoring the ship that first detected it. This discovery was monumental because it didn't just reveal an extreme point on Earth. It proved that the deep ocean was far stranger and more dynamic than anyone had believed. Suddenly, scientists realized they had only scratched the surface of ocean exploration. They began asking new questions. What forces could carve such a trench? Could life survive under unimaginable pressure? And how many other secrets lay hidden in the vast, unexplored waters of our planet? The HMS Challenger expedition did more than discover a trench. It founded the entire field of modern oceanography. It showed that the ocean was not a still, lifeless void, but a rich, ever-changing realm filled with mysteries waiting to be uncovered. And with this revelation, humanity's fascination with the deepest part of the ocean was born. A fascination that would drive future explorers, scientists, and adventurers to push the limits of technology and human endurance as they attempted to unlock the secrets of this profound abyss. After the groundbreaking findings of the HMS Challenger, scientists around the world knew the oceans held far more secrets than anyone had dared to imagine. But although the 19th century rope-sounding method had revealed the existence of the Mariana Trench, it was slow, imprecise, and limited by the strength of the materials used. Humanity needed a better way to measure the hidden world beneath the waves, a way that didn't rely on miles of rope sinking blindly into the abyss. And as the 20th century unfolded, a new technological revolution emerged: echo sounding. Echo sounding transformed ocean exploration from guesswork into precision science. Instead of lowering weighted ropes, ships sent powerful sound pulses into the depths. These sound waves traveled downward until they struck the seafloor, bouncing back to the surface like an acoustic mirror. By timing how long the echo took to return, scientists could calculate depth with incredible accuracy. This single invention changed everything. Suddenly, the ocean floor was no longer a mystery of darkness and imagination. It became a landscape humans could finally map realistically. As oceanographers began using this technology, they discovered that the Mariana Trench was even deeper than previously believed. The earlier rope measurements, while impressive, had underestimated the true scale of the abyss. Echo sounding revealed that the Challenger deep plunged to depths greater than 7 miles, making it the deepest natural point on Earth. These numbers were more than scientific data. They were a window into a world few had ever dreamed existed. In the early 1950s, the British vessel HMS Challenger II returned to the region with improved equipment and a mission to recalibrate earlier findings. When the crew directed their echo sounders into the dark water, they recorded readings that pushed the limits of what oceanographers considered possible. The depth markers kept dropping, revealing the trench's staggering descent. When the final calculations were confirmed, scientists realized they were observing one of Earth's most extreme environments, a place shaped by unimaginable geological forces. But the new data also hinted at something even more intriguing. The complexity of the trench's shape suggested that the seafloor was not static or simple. Instead, it was being constantly reshaped by tectonic processes far below the crust. The Mariana Trench was formed by the Pacific Plate sinking beneath the Philippine Plate, dragged down by the slow, relentless motion of Earth's lithosphere. This process, known as subduction, carved a trench so deep and so dramatic that even modern technology struggled to measure it fully. Yet, while the numbers were astonishing, the human reaction was even more profound. Scientists realized that if the Earth could form a trench deeper than Mount Everest is tall, then the deep ocean was a frontier every bit as compelling as outer space. The Challenger? Deep was not just a location. It was a symbol of the vast and largely unexplored mysteries of our own planet. And for the first time, humanity was developing the tools necessary to uncover those mysteries with clarity and confidence. Echo sounding did more than refine our understanding of ocean depth. It ignited a new era of exploration. As governments, research institutions, and private innovators began investing in deep-sea technology, the race to explore the Mariana Trench grew more intense. What had once been an impossible dream was now becoming a scientific challenge. The ocean was calling, and the world was finally ready to answer. The revelation of the Mariana Trench's true depth pushed scientists to confront a terrifying question. What really happens in a world so deep that sunlight has never touched it? As explorers pushed their calculations further, they began to understand the unimaginable conditions lurking inside the Challenger deep. Conditions that challenged the limits of life, technology, and even human imagination. The first and most daunting force in this abyss is pressure. As you descend through the water column, the weight of the ocean begins to stack above you layer by layer, mile after mile. At the surface, we live under a comfortable pressure of 1 atmosphere, but by the time you sink to the depths of the Challenger Deep, more than 7 miles down, the pressure reaches over 16,000 pounds for every square inch. That is the equivalent of placing several fully loaded passenger jets on top of a single human body. If you descended in a normal submarine, it would collapse like a tin can under a hydraulic press. This immense pressure creates an environment where only the most specialized organisms can survive. Instead of rigid bones or gas-filled organs, deep-sea creatures evolve soft, flexible bodies that squeeze and deform without breaking. Their cellular chemistry is tuned to resist crushing forces that would destroy the structure of normal biological molecules. Even their proteins are modified with unique stabilizers called piezolites, which prevent them from collapsing under pressure. Every organism that lives at these depths is a marvel of evolutionary engineering. Then there is temperature. Near the surface, oceans can be warm and vibrant with life, but as you descend, the temperature drops rapidly until it reaches near freezing levels. In the Challenger Deep, water temperatures hover just above 32 degrees Fahrenheit, creating a world of endless cold that slows metabolism and movement to the bare minimum. Life here must survive in a near-frozen state, conserving energy and adapting to an environment where every calorie matters. But the most haunting aspect of the deep ocean is the complete and permanent absence of light. Sunlight cannot travel more than a few hundred feet into the water. Below that, everything fades into blue, then into black. At the depth of the Challenger Deep, there is nothing but eternal night. Creatures here navigate a world devoid of color, shape, or visual cues. Many species lack eyes entirely, relying instead on vibrations, currents, and chemical trails to understand their surroundings. Others produce their own light through bioluminescence, creating ghostly flashes in the darkness as a form of communication, camouflage, or predation. Because of these extreme conditions, early scientists believed life could not exist in such a place. They assumed the deep ocean was sterile, a cold, empty realm untouched by biology. But as technology advanced and probes were slowly lowered into the abyss, they revealed a world filled with movement, mystery, and resilience. Tiny shrimp-like amphipods darted across the seafloor. Microbial communities thrived in sediments rich with chemicals carried down from the upper ocean. Even larger predators, adapted over millions of years, patrolled the cold, black expanse. Understanding the Challenger Deep meant acknowledging a hard truth. The ocean is not just deep. It is a vast, layered universe with its own physics, its own creatures, and its own rules of survival. And humans were only beginning to grasp how extreme, how alien, and how awe-inspiring this world truly was. As scientists revealed the harsh reality of the Challenger Deep, a new and electrifying question emerged. If such extreme conditions exist, then what sort of creatures could possibly survive there? The idea that life might thrive under crushing pressure, freezing temperatures, and total darkness seemed unbelievable. And yet, every descent into the trench uncovered evidence that life not only survives, it adapts in ways more extraordinary than anything found on the surface. Among the most surprising discoveries was the enigmatic Mariana snailfish. Unlike the sleek predators of the open ocean, the snailfish looks fragile, almost ghostly. It has a translucent body with no scales, jelly-like flesh, and bones so soft they bend with ease. But this softness is its greatest weapon. Without rigid structures that would shatter under intense pressure, the snailfish can glide effortlessly through the deepest waters. Its internal chemistry allows its cells to operate normally at depths where pressure would destroy ordinary life. Instead of gas-filled swim bladders, it uses gelatinous tissue for buoyancy, preventing deadly implosion. The snailfish feeds using suction, pulling tiny crustaceans from the seafloor with a quick burst of force. Its senses are adapted to the silent darkness, detecting subtle vibrations that reveal both prey and predators. The existence of such a creature shocked biologists. It proved that life finds a way even in places where physics alone seems determined to crush it. Then came the sightings of one of the deep's most mysterious inhabitants, the magna pinna squid, often known as the big fin squid. This creature appears more like something imagined in science fiction than a natural animal. With extremely long, elbowed arms that can stretch many times the length of its body, the big fin squid drifts through the water like a ghostly kite. Its movements are slow and deliberate, conserving precious energy in a place where food is scarce. Its flexible limbs hang straight down like long, shimmering threads, giving it an almost alien silhouette against the darkness. And yet, even stranger are the smaller, almost microscopic organisms thriving in the sediments of the Challenger Deep. Microbial communities live buried in layers of mud that have accumulated for millions of years. These microbes survive by breaking down chemicals that drift down from the surface or from hydrothermal vents far away. Their slow, patient metabolisms reveal a truth about life. It does not always need sunlight, complexity, or abundance. Sometimes, all it needs is time and adaptation. Deep-sea amphipods, tiny shrimp-like creatures, were also found thriving where few expected to see anything moving at all. Their bodies contain unique compounds that allow their proteins and membranes to resist intense pressure. Some even carry pigments that protect them from faint radioactive particles that exist naturally in the sediments. These amphipods are vital scavengers, feeding on organic matter sinking from far above, including the remains of fish, plants, and marine snow drifting down like cosmic dust. What these creatures reveal is a profound message. The deep ocean is not barren, but bursting with life uniquely crafted for survival in conditions that would annihilate most known species. Each organism represents millions of years of evolution sculpted by darkness, pressure, and scarcity. Their existence expands our understanding of biology and forces scientists to reconsider the limits of life, not just on Earth, but on other worlds as well. As explorers stared into the grainy footage transmitted from the abyss, one thing became clear. The Challenger Deep was not a silent tomb. It was a living, breathing ecosystem shaped by forces beyond human experience, inviting researchers to search deeper and uncover what other secrets the darkness might hold. By the mid-20th century, the Challenger Deep had evolved from a scientific curiosity into one of the greatest challenges of human exploration. Researchers had mapped its depth with echo-sounding, uncovered life in its impossible environment, and pieced together the tectonic forces that carved this colossal scar into Earth's crust. But one question remained unanswered, a question that burned in the minds of scientists, engineers, and adventurers alike. Could a human being actually reach the bottom? This question seemed almost absurd at the time. The pressure alone was enough to crush steel. No existing submarine was built to withstand forces that could warp metal like soft clay. Reaching the Challenger. Deep required a machine unlike anything the world had ever seen, a craft capable of resisting pressure greater than 16,000 pounds per square inch. It demanded engineering solutions that bordered on the impossible. Enter the Trieste, a vessel that would redefine exploration forever. The Trieste was unlike any submarine. Instead of relying on a long metal hull, it used a massive gasoline-filled float connected to a spherical pressure chamber made of thick steel. Gasoline, being lighter than water and nearly incompressible, provided perfect buoyancy. The sphere, only large enough for 2 people to squeeze inside, had walls thick enough to resist the crushing weight of the deep. It was cramped, cold, and claustrophobic, with barely enough room for the pilots to move. But it was also humanity's best chance at reaching the deepest point on Earth. On a quiet morning in January of 1960, ocean explorer Jacques Piccard and U.S. Navy Lieutenant Don Walsh climbed inside the Trieste. As the hatch sealed shut above them, they knew they were embarking on a descent never attempted in human history. The world watched with breathless anticipation as the vessel began its slow fall into the darkness. As the Trieste sank, the sunlight faded within minutes, swallowed by a growing blackness that felt endless. The pressure mounted steadily, squeezing the sphere from all sides. As the descent continued, something terrifying happened. At around 6 miles down, the men heard a loud cracking noise, the sound of one of the vessel's plexiglass observation windows fracturing under the enormous pressure. For a moment, the mission seemed doomed, but the crack did not spread, and the Trieste continued downward into the abyss. After nearly 5 hours of descent, the craft finally touched the seafloor of the Challenger Deep. For the first time in human history, 2 people were sitting at the very bottom of Earth's ocean. The depth gauge indicated they were more than 7 miles below the surface. The pressure outside was unimaginable, enough to crush any conventional submarine instantly. Yet inside the steel sphere, Pickard and Walsh remained safe, staring into a landscape that no human eye had ever witnessed. The seafloor was surprisingly soft, covered in fine sediment that billowed like smoke with the slightest movement. Visibility was limited, but something extraordinary happened. The men reported seeing a flatfish-like creature resting on the seafloor. If accurate, this sighting would challenge everything biologists believed about the limits of life. While later evidence cast doubt on the exact species they saw, the possibility alone sparked new debates about the resilience of life in extreme environments. After only 20 minutes on the bottom, the explorers began their ascent. Their mission had succeeded. Humanity had touched the deepest known part of the ocean. The Trieste's achievement was more than a technological triumph. It was a statement, a declaration that human curiosity has no boundaries. The descent proved that with enough determination, innovation, and courage, even the darkest and most hostile places on Earth could be reached. And yet, this was only the beginning. The Challenger Deep still held secrets waiting to be discovered, and new explorers were already preparing to push the limits even further. After the Trieste's legendary descent in the year 1960, the Challenger Deep remained untouched by humans for decades. The technology of the time had reached its limit, and although the achievement was monumental, the world was not yet ready to push deeper into routine deep-sea exploration. The abyss waited in silence, unvisited, mysterious, and largely unchanged. But while humans stayed away, technology evolved, quietly, steadily, and relentlessly, until a new age of exploration dawned. By the early 21st century, the dream of returning to the Challenger Deep had been revived. Advances in engineering, materials science, and robotics meant humanity finally had the tools to build submersibles capable of reaching these crushing depths repeatedly and safely. And at the forefront of this modern age stood a man known for his curiosity, creativity, and relentless passion for exploration: James Cameron. Most people knew Cameron as a filmmaker, the visionary behind some of the greatest cinematic achievements in history. But behind the camera, he was an engineer, inventor, and deep-sea explorer, with a long-standing fascination for the mysteries of the ocean. For him, the Challenger Deep was not just a destination, it was the ultimate frontier. Working with a team of scientists and engineers, Cameron helped design a groundbreaking submersible called the Deep-Sea Challenger. It was a sleek, vertical craft built specifically for the extreme pressure of the abyss. Its core structure relied on advanced syntactic foam, one of the only materials capable of withstanding the immense forces at 7 miles down. Every bolt, battery, and camera system was engineered for survival in a world where pressure could crush steel like soft clay. On a historic day in March of 2012, James Cameron became the first person in history to complete a solo descent into the Challenger Deep. As the submersible dropped through the layers of the ocean, he felt the same mix of tension and wonder that Pickard and Walsh had experienced half a century earlier. Darkness swallowed the craft, temperature plummeted, Pressure climbed to unimaginable levels. But unlike the Trieste, the deep-sea Challenger was built not just to reach the bottom, but to explore it. When Cameron finally touched down on the seafloor, he found himself standing at the edge of an alien world. The ground was pale, flat, and fine-grained, shaped by centuries of drifting marine snow. The submersible's lights revealed a quiet, eerie landscape stretching into the darkness. For several hours, he maneuvered across the seafloor, capturing high-resolution footage, collecting samples, and documenting the geology of the trench. His mission wasn't just about breaking records. It was about gathering scientific data that could reshape our understanding of deep-sea ecosystems. One of the most remarkable outcomes of Cameron's dive was the discovery of organisms with unique biochemical properties. Some of these microbial samples were later studied for potential medical breakthroughs, including compounds that might help treat diseases such as Alzheimer's. The Challenger Deep, once thought to be a lifeless void, was now recognized as a treasure chest of biological potential. But the Deep-Sea Challenger mission did something else. It reignited global interest in the abyss. It reminded the world that exploration is not just about conquering physical limits. It is about expanding human knowledge and understanding. Cameron's success paved the way for a new generation of explorers, engineers, and scientists who were ready to pursue the trench with renewed ambition. And soon, one explorer would go even further, not just diving once, but many times, turning the deepest point on Earth into a site of continuous discovery and groundbreaking research. After James Cameron's historic solo descent in 2012, the Challenger Deep entered a new era of exploration. Yet while Cameron proved a single human could reach the abyss safely, there was still much to learn. Repeated dives were necessary to study its ecology, geology, and the unexpected consequences of human activity. This is where adventurer and explorer Victor Vescovo took center stage. Vescovo, a retired naval officer and professional explorer, designed and piloted the DSV Limiting Factor, a full ocean-depth submersible engineered to dive to the deepest parts of every ocean on Earth. Unlike the Deep-Sea Challenger, which was a one-time expedition, the Limiting Factor was built for repeated missions. Its titanium hull, advanced buoyancy systems, and cutting-edge electronics made it virtually indestructible under extreme pressure. Over several years, Vescovo completed multiple dives to the Challenger Deep, setting new records and gathering an unprecedented collection of data about the trench. During these dives, Vescovo and his team confirmed that life was thriving even under conditions that were once thought completely inhospitable. Strange, gelatinous creatures drifted in the darkness, shrimp-like amphipods crawled across the sediment, and previously unknown species were documented, demonstrating that life adapts in extraordinary ways to the crushing pressure, freezing temperatures, and complete darkness of the abyss. Yet exploration revealed another, far more alarming truth. Despite the extreme remoteness of the Challenger Deep, human pollution had reached even this untouched world. Plastic debris, from packaging fragments to fishing gear, was found scattered along the seafloor. These discoveries were shocking. Many had assumed that 7 miles below the surface, far from any human activity, the trench would remain pristine. Instead, Vescovo's dives revealed a sobering reality. No corner of Earth's oceans is truly free from human impact. This finding sparked global concern among scientists and environmentalists. If plastic could reach the Challenger Deep, carried by currents and sinking from the surface, what did this mean for ecosystems elsewhere in the ocean? How would these foreign materials affect organisms that had evolved for millions of years in isolation? The Challenger Deep, once seen only as a symbol of natural wonder, now became a stark reminder of human responsibility and environmental stewardship. Alongside ecological insights, Vescovo's missions offered unprecedented geological observations. The trench's sediment layers told a story of tectonic motion and ancient earthquakes. Deep faults and subduction zones were mapped in detail for the first time. These discoveries provided invaluable information for understanding not only the Mariana Trench, but the mechanics of plate tectonics worldwide. In addition, repeated deep dives allowed scientists to study adaptations of deep-sea life more thoroughly. For example, they could observe how the Mariana snailfish and other species moved, fed, and reproduced in their extreme environment. Each dive expanded our understanding of biological resilience and evolutionary ingenuity. Researchers began to see patterns, drawing links between species, chemical compositions, and energy sources, painting a picture of a self-sustaining ecosystem at the bottom of the ocean. Yet, despite all these discoveries, the Challenger Deep retained its aura of mystery. Every expedition revealed wonders, dangers, and surprises, but still, much of the abyss remained unexplored. It was a reminder that no matter how advanced human technology becomes, the ocean's deepest recesses are a frontier as formidable and enigmatic as outer space. Vescovo's record-breaking dives symbolized humanity's relentless pursuit of knowledge, but they also underscored a difficult truth. The deeper we go, the more we see how fragile and interconnected our world truly is. The Challenger Deep is more than just the deepest point on Earth. It is a natural laboratory for understanding life in extreme environments. Scientists quickly realized that the extreme conditions of the trench, total darkness, freezing temperatures, crushing pressure, and scarce nutrients, mirror the environments we might encounter beyond our planet. For organizations like NASA, studying these extreme habitats is essential for preparing humanity for the challenges of space exploration. NASA's interest in the deep ocean is twofold. First, the Challenger Deep serves as an analog environment for extraterrestrial worlds. For example, moons, such as Europa around Jupiter and Enceladus around Saturn, are believed to harbor subsurface oceans beneath thick ice layers. If life exists in these distant oceans, it would need to survive conditions similar to those in the Mariana Trench: extreme pressure, no sunlight, and limited food sources. By observing how life adapts on Earth, scientists can formulate hypotheses about the possibility of life elsewhere in our solar system. Second, the trench provides an opportunity to test technologies that might be used in space missions. Submersibles like the Deep-Sea Challenger and the DSV limiting factor operate in environments with high pressure, limited communication, and complete darkness, conditions not unlike those spacecraft face in deep space or under icy crusts. Cameras, sensors, robotic arms, and life support systems developed for the deep ocean are now informing the design of spacecraft intended for exploring other worlds. The challenges of the deep sea offer lessons in engineering resilience, remote operation, and long-duration missions. Explorations in the Challenger Deep have also revealed biological insights relevant to astrobiology. Microbes living in sediments, crustaceans adapted to extreme pressure, and unique biochemical adaptations provide models for what life might look like beyond Earth. Molecules evolved to withstand crushing pressure or extreme cold might inspire future bioengineering or pharmaceuticals. Understanding the physiology of these organisms informs our expectations of extraterrestrial biology and the search for biosignatures in alien oceans. Moreover, the trench offers a controlled yet natural environment for studying human survival and operation in extreme conditions. Pilots, engineers, and scientists learn to navigate challenges similar to those that might occur on space missions. Limited maneuverability, high-risk equipment failure, and reliance on life support systems that must perform flawlessly under pressure. Each descent into the abyss teaches lessons that go beyond oceanography. They prepare humans for exploring worlds where the stakes are equally high. NASA's involvement in deep-sea research also demonstrates the synergy between different scientific disciplines. Oceanography, geology, biology, and engineering converge at the Challenger Deep, creating a multidisciplinary approach to exploration. Data from the trench feeds models of planetary science helps design autonomous exploration robots and contributes to environmental science by tracking pollution even in remote ecosystems. Ultimately, the Mariana Trench is more than a remote oceanic depression. It is a proving ground for scientific curiosity, technological innovation, and the quest to answer one of humanity's most profound questions: are we alone in the universe? Every plankton, snailfish, and sediment sample collected from the abyss not only expands our understanding of Earth's oceans, but also brings us closer to discovering the potential for life in worlds beyond our own. The Challenger Deep, with its unfathomable darkness and near impenetrable depths, has long captured the human imagination. While scientists focused on mapping, diving, and understanding its geology and biology, popular culture took a different path, one filled with mystery, speculation, and wild theories. Legends of giant sea monsters, secret government bases, and hidden civilizations began to circulate, fueled by the trench's extreme inaccessibility. One of the most persistent myths is that of giant sea creatures lurking in the depths. Stories of monstrous predators, some claiming to be remnants of prehistoric species like the megalodon, emerged in books, documentaries, and online forums. The logic seemed plausible at first. The ocean is vast, dark, and largely unexplored, so why couldn't gigantic creatures exist miles below the surface? However, scientific evidence paints a very different picture. The extreme pressure at the Challenger Deep, over 16,000 pounds per square inch, would make it impossible for any large vertebrate, such as a giant shark, to survive. Only small, highly specialized organisms can endure these conditions. Soft-bodied creatures like the Mariana snailfish or gelatinous squids thrive, but they are nowhere near the size of mythical monsters. Another enduring theory involves secret military or research installations hidden in the trench. Conspiracy theorists claim that governments have built underwater bases to conduct experiments, store weapons, or hide classified technology. While imaginative, these ideas do not withstand scrutiny. The Challenger Deep is one of the most remote and inhospitable environments on the planet. Constructing and maintaining a habitable base at 7 miles below sea level, under crushing pressure, freezing temperatures, and total darkness, is far beyond current engineering capabilities. Every expedition, whether by Trieste, Deep-Sea Challenger, or DSV limiting factor, has shown only natural geological formations and marine life, not human structures. The persistence of these myths says more about human curiosity and fear than about reality. The trench's darkness, immense scale, and inaccessibility naturally invite speculation. When no human eye can observe a place, the imagination fills the void. This is why popular culture often prefers dramatic interpretations over scientific explanation. Science, however, provides clarity. Detailed sonar mapping, robotic exploration, and manned descents have confirmed the Challenger Deep's geology and biology. Plate subduction explains its formation, with the Pacific Plate sliding beneath the Philippine Plate, carving the trench over millions of years. Sediment layers, fault lines, and microbial communities have all been studied extensively, revealing a dynamic, natural environment. Every exploration has emphasized that life exists here, but in forms adapted to extreme pressure, cold, and darkness, not in the shape of fantastical monsters. Debunking these myths is not about dismissing wonder, rather, it enhances it. The real discoveries of the Challenger Deep, resilient snailfish, bioluminescent squids, microbial life thriving under pressures that would crush humans, are far more awe-inspiring than fiction. Life's ability to adapt to such hostile conditions is a testament to evolution's power and the ocean's untold mysteries. Even as conspiracy theories persist online, the Challenger Deep stands as a symbol of scientific rigor. Every mission, every dive, every sample collected reinforces a critical lesson. Curiosity must be paired with evidence. By separating fact from fiction, humans can truly appreciate the extraordinary natural world that exists in the deepest corners of our planet. As humanity returned repeatedly to the Challenger Deep, the abyss revealed not just the extraordinary adaptations of life, but also the pressing realities of our impact on the planet. Modern explorers like Vescovo have transformed the deepest part of Earth into a living laboratory, continuously expanding our understanding of geology, biology, and environmental science. Each dive uncovers sediment layers that record Earth's tectonic history, unknown species that demonstrate the limits of evolution, and increasingly, evidence of human influence, even in the planet's most remote corners. One of the most sobering discoveries is the presence of plastic debris scattered across the seafloor. Fragments of bags, fishing lines, and microplastics have been found even at depths exceeding 7 miles. This reality challenges the notion of untouched wilderness, proving that no environment is truly isolated from humanity's reach. Scientists now study how these pollutants interact with deep-sea ecosystems, potentially affecting microbial communities and food chains in ways we are only beginning to understand. Simultaneously, continued exploration has revealed life forms more remarkable than ever imagined. Gelatinous organisms drift through the abyss, using minimal energy to survive. Shrimp-like amphipods scavenge microscopic particles from sediment. The Mariana snailfish continues to astound researchers with its adaptations to survive in crushing pressure and total darkness. Each new species recorded reinforces the idea that the Challenger Deep is not barren. It is a thriving ecosystem, finely tuned to extremes that would destroy almost all surface life. The trench also serves as a testing ground for technology. Submersibles like the DSV limiting factor employ titanium hulls, advanced buoyancy systems, and robotic tools that operate flawlessly under enormous pressure. The lessons learned in these extreme conditions inform broader engineering challenges, from deep-sea resource management to outer space exploration. NASA and other research institutions study the Challenger Deep as a natural analogue for extraterrestrial oceans, like those on Europa or Enceladus, helping scientists prepare for missions that might one day search for life beyond Earth. Yet the Challenger Deep is not merely a site of scientific fascination. It is also a symbol of responsibility. The stark contrast between thriving deep-sea life and the visible human pollution reminds us that our actions resonate far beyond our immediate environment. Protecting these fragile ecosystems requires both awareness and action, from reducing plastic use to supporting global efforts for ocean conservation. Ultimately, the Challenger Deep is a frontier in every sense. It embodies the mystery, danger, resilience, and wonder of Earth's oceans. Each exploration deepens our knowledge, challenges our assumptions, and inspires awe at the tenacity of life in extreme environments. The trench connects human curiosity with the broader quest to understand life on Earth and elsewhere in the universe. It is a place where scientific discovery, environmental stewardship, and imagination converge, reminding us that even the darkest corners of our planet are alive with meaning and possibility. Thank you for joining us on this incredible journey to the Challenger Deep, the deepest, most mysterious point on our planet. From historic discoveries to record-breaking dives and astonishing life forms, we've seen how the ocean's abyss connects science, exploration, and environmental responsibility. If this voyage inspired your curiosity and sense of wonder, Make sure to subscribe and join us for more adventures into the hidden corners of our world. The ocean is vast, and every dive brings us closer to understanding its secrets, and maybe even the mysteries of life beyond Earth.